Good afternoon, everyone. Hi, my name is Lee Lind, for those of you who I don't know, and I'm on the faculty here. And it's my great pleasure to welcome you to the Jones Seminar Series and to introduce today's speaker. Dr. Jifeng Liu is a postdoctoral associate at the Massachusetts Institute of Technology, doing work in the Department of Material Science and Engineering. I'll let him introduce his work in more detail. Prior to beginning there at the end of 2006 in a postdoc at MIT, he was a graduate student in Material Science and Engineering at MIT. Also got a master's degree in Material Physics and Chemistry from Tsinghua University in Beijing, and then a bachelor's in Material Science also from Tsinghua University, and that was in July of 1999. So, without further ado, Jifeng, it's great to have you with us, and we look forward to your talk.
Thank you very much. So thanks for the introduction, and I would really like to, take this opportunity to also thank the Faculty Research Committee for inviting me here, and also I would like to thank the faculty members and students who I met in the past 2 days. It's really exhilarating experience. Thank you very much for coming. So today I'm going to share with you our knowledge and research on nanophotonics, that is manipulating light at nanoscale for applications in energy sustainability. As we know, energy has become a critical issue in the 21st century, and in terms of energy sustainability, there are basically two aspects. One aspect is to enhance the energy efficiency of existing system. That is to do the same job with less energy, and the other side is to produce this renewable energy in a low-cost fashion so that it can become competitive with fossil fuels in terms of electricity generation. So in this talk, I'll touch on both aspects. First aspect is about integrated photonics on silicon. The benefit there is that it really reduces the energy consumption that you transfer data from one place to the other. It turns out in our information age, the energy consumption by information technology is a fast-growing factor. And interconnect, that means transmitting the data from one place to the other, actually takes a large portion of the energy consumption. So we are using photonics to minimize that part. And the other side is about the solar cells. So we know that solar cells is a really good renewable energy harvest apparatus. However, we need to reduce the cost to make it more feasible and competitive with fossil fuels. So here, what we have here is that instead of using a bulk silicon wafer as people used to do with solar cells, we're now using a very thin layer of silicon. The benefit there is that you really throw away that material cost, which is half of the solar cell module cost for now, and also you reduce the cost of processing, because this thin film deposition is a very low temperature process, about relatively low temperature process, about 300 degrees, while the bulk silicon you have to go to 1,000 degrees to get the material. So it can potentially give you a significant reduction in the cost. However, because your optical path is only limited by the film thickness, we are designing some nanophotonic structures to diffract the light sideways so that they can elongate their path length in this film. So you can keep the same efficiency with much less material, much less cost, and that will help you to get renewable energy competitive to the existing fossil fuels. So here's the outline of this talk. I'll start with talking about monolithic nanophotonics for green information technology. That's to minimize the energy consumption that we have in the information technology systems while still enjoying the benefits of high bandwidth that you're enjoying now. I'll talk about the motivation for electronic-photonic synergy for this kind of achievement. But I'll next go through the devices for this technology. And we'll particularly go through photonic nanowires. That's the wires we use to carry the photons on a silicon chip. High-speed photovoltaic photodetectors that can convert your optic signals to electrical ones at very high speed. And it has a photovoltaic effect. So it can actually generate power instead of consuming power. We talk about low energy consumption photonic modulators. That's the workhorse you use to generate binary information in optics domain. I will show you that this can be made very small and very efficient. I'll finally talk about our ongoing work of doing monolithic lasers, which is sort of a holy grail for silicon photonics. Then I'll go through the nanophotonic structures for the other side, clean energy harvest and recycling. We'll talk about solar cells, and we also talk about thermal photovoltaic cells. This can be used to recover the waste heat generated in your furnaces. So you can turn that heat radiation directly into electricity, and this will also save the energy consumption. So let's start talking about how much energy do we have to use for information technology systems. We all enjoy the benefits of computers, internets, iPhones, iPods, but few of us think about how much energy we do consume in this technology. So I would like to ask a question to the audience. Anyone has any idea how much percentage of energy your brain consumes?
30%.
That's a very good number, actually. So it's greater than 20% from different sources. I think 30% may be a very good estimate. And human brain is only 2% of the body weight, but it consumes over 20% of the energy. So that tells you processing and transferring information can actually cost much more energy than you ever imagined. And as we go through this information age, we have more and more growth in this information technology. We have huge demands for data transmission. Actually, Google says that the online data transmission is increasing by 95% per year. That's almost doubling every year. Data storage is increasing by 60% a year. So we need to build more things like these data centers to accommodate that. So this is what the data center looks like. You have racks of computers here, and this is usually situated in a pretty large building. Outside this building is actually a system for electricity generation, because each of this thing will cost you 10 million watts to run. So if you look at data center power consumption versus the total electricity for United States, Japan, and the world, you'll find in 2000, this has already reached 0.6%. This is actually pretty amazing, because when do we have internet, right? We had internet in the mid-90s. Just a few years we have internet. 5 years later, in 2005, this percentage doubled. 2006, we have 1.5%. And Japan is even a little bit more than that, because Japan actually have many plans for high bandwidth connections with HD TV. And if we continue this trend, just the data center alone will consume 100% of our electricity production by 2035. So that's in 25 years. So it's no surprise that Dr. Chopra, Virginia's Secretary of Technology, says data centers are really the energy hogs of the 21st century. Please note there's no other industry grow quite at the rate as the information technology in our century, because we are in the information age. Associated with that energy consumption, it is estimated 1 billion tons of CO2 is generated by IT industry this year. So from environmental point of view, we have to minimize the energy consumption and do things in a more energy efficient way. So why do we have so much energy consumption here? Part of the issue can be found if you look to the backside of these cabinets. You find tons of these cables, these all copper cables. Those are connecting the computers from rack to rack and also from cabinet to cabinet. As you have these metal wires, you pass a current through that. There are several limiting factors. First, when you want to do this at high data rate, you have resistance capacitance related delay. It takes time to charge and discharge, so that's limited the data rate you can transmit. And you always have resistance there, so you have resistive loss. Associated with that loss is heat dissipation. So everyone has the experience how hot your laptop can get, right? So this is the heat dissipation from that. And you have all these copper cables, which is heavyweight, and they're pretty dense too, so they block the airflow. So actually in this data center I showed you in the previous picture, almost half the power is, and 2/3 of the space is due to air conditioning and cooling. So if we can get rid of this copper wires and connect things in a more efficient way, then we are going to get a big plus in energy efficiency. So in your computer, the same thing is actually also happening. So this is what we call interconnect bottleneck on silicon chips. In the figure on the left, this vertical axis is delay. You can see there are two kinds of delay. One is due to the transistor processing speed, which is called gate delay. It's actually decreasing when you go to nano because your gate width that electrons have to transit to process the information is getting lower and lower. However, not everything gets better with nano. For example, you take a wire, you shrink its cross-sectional dimension. You know from engineering 101 that it's going to increase the resistance. And also, as you pack the wires more closely, you get more capacitance. So that's exactly what has driven us from aluminum metal and SiO2 layer to a copper metal and low dielectric constant layer. Copper used to be a big taboo in silicon microelectronics. And the reason is that, for those of you who are familiar with semiconductors, copper is a deep center in silicon. And that will really deteriorate your device performance. So people have got great efforts to bring copper into silicon transistors just for this reason. So, but even with copper, you can see that overall delay still increase as we go beyond the 100 nanometer node. We're currently at 45 nanometer node. So people find we have a diminishing return as we shrink the transistor size due to this delay. Even more critical issue is this power density. So the total length of metallic wires on a chip has now exceeded 20 miles. So just imagine, put 20 miles of wires, you wind it around and put in a chip, which is about 2 centimeters square. And you pass current through that. That's effectively a hot plate. So that's exactly why the frequency scaling stopped around 2004. For those of you who remember the 90s, 1995, we only have a computer of frequency 100 megahertz. By 2001, already increased by 10 times. Five years, we increased by 10 times. 2004, we have 2.5 or 3 gigahertz. So Intel actually has a plan to increase it to 4 gigahertz. And what happens is that you have so much heat dissipation, you're approaching the power density level around 100 watts per centimeter square. And there's no really economic way to cool your chip anymore. So your fan doesn't work anymore. You have to go to liquid nitrogen. What does this number mean? So give you some feeling. On a sunny day, solar radiation intensity is about 0.1 watt per centimeter square. So this is 1,000 times concentration of the solar power density. That's equivalent to putting a magnifying glass and focus it to a small spot. And I think most of you have done experiments before, right? You can really burn something with that. So if you do not want to order liquid nitrogen for your computer, you do not want to scale your frequency anymore. So what's the solution for that? Starting from there on, we're actually looking at this multiple core processors. However, please note that 60% of the total power consumption is still due to the interconnects, due to the copper wires on the chip, transferring data from one place to another. So even with multi-core, you still have to address this issue. So people do have a roadmap, just like Moore's law scaling, doubling the number of cores every 18 months. So you probably do not see like 8-core, 16-core processors on the market, but actually in research level, MIT has developed a 16-core processor in 2002, and over time, industrial people have been doing research on multi-core processors. In 2007, Intel did this 80-core processor, but guess what? They cannot really run this processor. They do not work because they haven't figured out a way how to connect these cores to the memory efficiently so that it can transmit high-speed data. For electrical to do that, you have to bring the memory very close to the, to the CPU so that you can minimize the RC delay. But it's not until early this year that Intel figured out the only way to do that is to get 3D stacking of memory. So you put stacks and stacks of memory on top of your chip. However, the trade-off is that your power dissipation per unit area goes sky high again. So do we really have a solution for that? Well, we do. We're actually using that every day. So this chart basically plots the relative information capacity starting from the time when Alexander Bell invented telephone lines in late 1800s. And for 100 years, we see this curve growing. And all of a sudden, around 1980, we have a huge jump in terms of information carrier capability. And that's because of the Nobel Prize of this year, which is optical fiber. So instead of carrying information with a metallic wire, we're now carrying information with photons. And this photonics wires, there's no resistive heating, no RC delay. And one very beautiful thing about photons is that you can combine photons of slightly different wavelengths together into the same photonic wire without interfering each other. That's called wavelength division multiplexing, and it's shown in the curve right here. So the more wavelengths you put inside, the more channels you have, and your channels are color-coded so they don't intermix, and then you can really increase your capability of data transmission. So it's just instructive to see when did this happen. It happened at a bandwidth distance product of 10 megabits per second times kilometer. This parameter is relevant because electrical interconnect will power when we have high bandwidth or long distance. Let's do some arithmetic and rearrange it. This number is equal to 10 gigabits per second times meter. That's like the data rate and distance we use in data centers. So this is our Datacom goal. And this is also equal to 1 terabits per second times centimeter. This is about a goal we want to achieve on chip in this century. So from historic trend, we can see it is time to light up the chips and bring photonic interconnect to shorter distances. And I'll show you later that this will enhance your energy efficiency in data transmission by 100-fold. So photonics are good. Why don't we use it everywhere? So this figure shows you the reason. The age of photonics before it is pretty much similar as the electronics in 1940s. So devices are discrete. So you have laser, you have a bunch of fiber, you have modulator is the tool you encode signals into optical domain, and you have photodetector which converts signals from optical back to electrical. These things add up are much more costly than the CPU chip you have. So you cannot use this optics anywhere. So what's the solution? Just as the integrated electronics, we're now integrating these photonic devices on chip. You know the effectiveness of integrated electronics. We used to have radios in 40s, maybe this big, and something that can put your suitcase and bring on your car is already called portable. Nowadays, what is portable? It's something in your pocket, right? Like this size is portable. So that's the power of integration. The same thing will happen in photonics. As you decrease the device size, the capacitance will decrease, and in turn, your power consumption at high frequency operation will decrease. And also, the performance of some of the devices, especially the photodetectors, can be greatly enhanced. So integrating these photonic devices on a silicon platform that employs the merits of photons in data transmission with the merits of electrons in data processing is the promise for the future. So that's why Intel predicted in this April, silicon photonics will become one of the top 10 most important IT technologies in the next decade. Okay, we'll go through some of the really important photonic devices here. So we'll start with talking about wires. So just like electronics, you have copper wires. Photonics also have a wire, but it's guided by the index difference through the total internal reflection. So basically you have a core material with an index higher than the cladding, and when the total internal reflection angle is when the incident angle is larger than total critical angle for total internal reflection, then you get waveguiding in this wire. But the problem with the optical fiber is that this index contrast is very small. So your core index has to be large. It's 10 microns. And you cannot bend it very sharply because then the total internal reflection condition is not met, and then the light will leak out. So to miniaturize your photonic wire, we're actually using silicon as a core and silicon dioxide as the cladding. The index difference is very large, so that you can make a small core device. This is sub-micron or in nanometer level. So many of my colleagues call this photonic nanowire. This allows you a bending radius about 1 micron. So you may wonder, silicon is obviously opaque to light. So why do you use to transmit light? Actually, that's because we are using an infrared wavelength in which silicon is super transparent. It's more transparent than the regular glass in your window. So this will allow very low loss and very small dimension. You may also wonder that this one is still very thick. This is about 400 nanometers. While we have electric wire of only 45, so why this one is more powerful? Don't forget, we can put thousands of wavelengths in this single waveguide. So if you divide the width, each channel is 0.4 nanometers. Okay? So that's about the lattice constant of a material. So that level is very, very hard to achieve with electronic approach. So how about active devices? Active devices in photonics usually refer to lasers, modulators, and photodetectors. We're using actually a material that's already being used in silicon microelectronics, which is germanium. Germanium is doped into silicon to create strain in the silicon layer to enhance the mobility of carriers so that it can run faster. On the other hand, there's a very nice property of germanium in that it's a pseudo-direct gap material. So if you look up germanium band gap in the textbook, they usually tell you this number, which is an indirect gap transition. So in this chart, vertical axis energy, horizontal axis is crystal momentum. So in order for transition to happen, you not only need to match the energy difference, but also need to match the momentum. Why is indirect gap material inefficient in light emission or absorption? Because a photon cannot provide enough momentum to complete this transition. To complete this transition, you need additional help, and this help is the wave vibration in the lattice. So if you catch upon this wave, they will transfer enough momentum to you so that you can complete this transition. You can think about the penguins who want to jump onto an island that you see in the National Geographic Channel. So penguins are obviously not very good at jumping. So they have to catch the wave and get there. That is very inefficient. You have to wait. You cannot jump directly, okay? While in the direct gap, here, you can make a direct jump. So this gap is very efficient in light emission and absorption. So if you can utilize this one, We can do monolithic photodetectors and modulators. And if we do some further band engineering, we have a promise to do light emitters on silicon too from this direct gap transition. One of the tricks you can play is to apply tensile strain onto germanium. So you stretch the lattice. What happens there is that if you apply enough strain, then there's a crossover between this indirect gap and direct gap. So that means it effectively becomes a direct gap material because the minimum value is here. You can think about this as a bowl, and when you pump electrons inside, it's like filling water into this bowl. So if this value is minimum energy, then electrons will go here, and then they can emit light efficiently. Okay. So how do you introduce tensile strain? It's actually very simple. So we grow a germanium layer epitaxially on silicon at high enough temperature. So the germanium film is relaxed at the growth temperature, and when you cool it down, because germanium has a larger thermal expansion coefficient than silicon, it tends to shrink more. But the silicon substrate is holding it back. So then you have a constraint, which is a tensile strain. So I think it's true that anytime you have a constraint, you get stress and strain. It's also the same in your life, right? So this right figure shows how you integrate this germanium silicon material into CMOS. What we do is we perform a selective growth. Instead of growing germanium everywhere on the blanket, we can actually open a little trench here with dielectric cover, and then germanium will grow selectively into this trench. This facet is due to the single crystalline nature of germanium, just as you see with diamond, because germanium is exactly the same crystal structure as diamond. Okay, and if you don't like it, you can actually polish it down, and this is a nice flat material you get, and you can make a device out of that. Okay. So in terms of device structure, we're thinking a universal scheme for both detectors and modulators that are coupled with this silicon nanowires. This is a schematic 3D representation. So the light can couple from a crystal silicon layer into a amorphous silicon layer. The reason why we do this coupling is that the amorphous silicon still tend to have more loss than perfect crystalline silicon. So we want to minimize this length. And then it couples to a piece of germanium longitudinally. When this piece of germanium is short enough, it's relatively transparent to the light. So when you apply the bias, you turn this material from transparent to opaque at a certain wavelength. Then you can perform modulation. In other cases, when you don't want to do the modulation, you just want to convert the photons into electron hole pairs, you can make this path longer. So you absorb all the photons, and then you get photocurrent. So this is a cross-section SEM picture. So you can see the germanium core is here, only 600 nanometer wide. So the benefit is that we can use the same device structure, same material, and one-step processing for both devices. So this picture basically shows the performance of integrated germanium silicon photovoltaic photodetector. I'll explain a little bit what is photovoltaic. So this is the responsivity. When you look at the performance of a detector, you look at how much current in terms of amps per unit power, optical power input you can get. And this is the curve you measure. And this corresponds to about 80% efficiency. You also want to know how fast this detector is. So you can shine a very short femtosecond laser pulse and monitor with very fast electronics to see how much what's the decay curve of the electrical response. And you measure a full width at half maximum, about 50 picoseconds. That's greater than 7 gigahertz bandwidth. And this is all measured at zero bias. So you do not need to bias the material to get this full responsivity. So it does not only not consume material, you can actually think about harvesting photonic energy from this device. For example, this shows the IV curve when we have a dark case, when 60 microwatt of optical input at 1550 is shining through the detector, you'll see this curve move down. So can you tell me where we can generate energy? Any students want to make a guess? Here? Okay, why?
45 degrees.
Why? Okay.
Might see you going in the opposite direction. So.
Exactly. So think about battery. If you want to convince yourself to just think about battery, that voltage and current is in different direction. The times together you get a negative number. That's net optical. That's net power output. While here you have 2 negative. Here you have 2 positive. So there's no power output. Okay. So this device demonstrates strong photovoltaic effect. It can be used to recover, recycle photon energy on chip. Whenever you have a scattering, you can put it nearby and recover some of the scattered optical power. While you cannot do the same with electrics, because when you generate heat, it's very hard to recover it back, because the heat temperature is not high enough. So you can use thermoelectric to recover some of them, but the efficiency is much lower than photonic approach. Okay, let's talk about modulation. So how do you modulate light? Basically, you can change the material properties in optical properties in 2 ways. One is that you can change the real part of the refractive index, which is delta n. But this change is relatively small. It's 10 to the minus 4. And this is just a phase change. So if we want to create 2 anti-phase waves and cancel each other to shut the light off, you have to elongate this device length. That's why traditional Mach-Zehnder interferometers usually have a length of millimeter scale. A more compact version of this phase modulator is doing a ring. So basically, you can, by controlling the index of the ring, you can control the coupling and decoupling of light from the waveguide to the ring and achieve modulation. But the problem is that this is a resonant device, so it only works at a very narrow wavelength range. While electro-absorption modulator is changing the absorption coefficient of a material under electric field, so you can turn the material from transparent to opaque by applying a bias here. So it's a very convenient device, very straightforward. You just put the material in between your input and output waveguide and apply the bias, and you can turn it on and off. And this is a pretty large effect, because your absorption coefficient change can be 100 to 1,000 inverse centimeter. So it's a very compact device, less than 100 micron long. And associated with that is low capacitance and low power consumption. And intrinsic response is very fast. It's a field effect, so the response time is intrinsically is less than 1 picosecond. So that's 1 trillionth of a second. So this is a very efficient technique to get high-speed modulation at low energy consumption. In terms of operation spectrum range, it's usually around 20 nanometers. So you can operate in a spectrum range, and if you divide the spectrum, you can do your wavelength division multiplexing. So these curves are some of the performances. So let me guide you through that. This figure shows basically the extinction ratio, means the on-off ratio of the modulator. So you want this one to be as high as possible. This red curve shows the insertion loss of the modulator. That's how transparent the device is when you don't apply the bias. So you want this one to be as low as possible. So overall you can work in a wavelength range around 1539 to 1553 nanometers. So what's the significance about 1550? That's the minimum loss wavelengths for coarse optical fibers. So that's why people use it for optical communications. So this is very relevant. And if you look at the capacitance of the device, it's actually very small. It's only 11 femtofarad. And the energy per bit at 8 dB extinction ratio, that's roughly the on-off ratio about 9 to 10. You only consume about 25 femtojoules when you transmit 1 bit of power. And later I will show you a comparison that currently electrical is actually in the picojoule per bit range. So that's almost 2 orders of magnitude enhancement. We published in this paper, this is for actually 1/2, because it's more conservative estimate, assuming that the modulator is turning on and off all the time. But on average in data transmission, that's half of the energy like this. The first prototype will measure bandwidth of 1 gigahertz, but it can really improve to around 100 gigahertz if you optimize the processing of devices. Okay. So let's talk about light emitters, which is the holy grail for silicon photonics. So how do we make germanium direct gap, as we talked about? We already talked about a trick of using tensile strain, so you already bring this two values closer. Again, think about this as a bowl with two bottoms. So now you want to fill electrons inside, but still, because this is lower, you fill electrons first into this valley, and after you fill quite a lot, you can go to this valley. That's no good. So our idea is actually fill this bowl bottom with electrons by n-type doping. So now your bottom is filled to here. Now you imagine pouring water into this bowl. They will equally go to this gamma valley and this L valley. Okay, so this bowl is actually leaking because they recombine with holes here. The direct transition recombines much faster than the indirect transition. So to keep the statistic, we have what we call Fermi statistics, or keeping the level flat for these two bottoms, the electrons in this L valley will tend to scatter to here and further recombine, and that will give you efficient light emission. For those of you familiar with semiconductors, you do worry about the free carrier loss in here, but our modeling has shown that this transition is so powerful that it's enough to overcome the loss in here, such that you can get net gain and probably you can get lasing. So the first thing we tried is to do the photoluminescence of the material. So basically you shine a different color of light and look at the light emission of the material around its direct band gap. In this case, around 0.77 electron volts. So you can see with the increase of doping, n-type doping level, you do fill up your bowl at the indirect bottom. So you get a strong increase in light emission intensity. This is experimental data versus theoretical modeling. They agree pretty well. And another interesting feature is that the light emission intensity actually increases with temperature. For those of you who are familiar with 3.5 semiconductor, it's usually the opposite way in 3.5. So you don't want to operate at high temperature. But here, thermal excitation is actually promoting electrons from this bottom to this bottom. So that's why you get an enhanced light emission at high temperatures. We have go up to 80 degrees C, and this intensity is still growing. So that means it's pretty robust to thermal fluctuation on chip. And recently, we also get this optical gain result. So what is optical gain? You have a pump power, you have a pump laser, the population invert the electron hole pairs in the conduction and valence bands. Because you invert it, there's less absorption than emission, then you get a net gain in the material. So this is exactly what you see here. We're doing experiment on a germanium microdisc. This is basically to eliminate growth defects and also to provide lateral carrier confinement. So at the same power, you generate more carriers per unit volume in this material. And this is a regular absorption curve without pumping. And with pumping, you can see the absorption goes to negative. And this error bar is actually a very conservative estimate. So even with this most conservative estimate, you still get a negative absorption coefficient around 1605 nanometers. That means you're getting gain. So you're not absorbing, you're actually amplifying the light now. So in principle, you can do a laser with this disk, but the index of germanium is so large that light is very hard to escape out. So what we do is that we did a very simple structure, a strip of germanium material, also selected chrome. We shine the pulse laser on it and monitor the light emission from the edge. So we see a typical lasing behavior. We start with this broad spectrum, and then we start to see features as we increase the pump power. And this features wavelength is actually consistent with the wavelength range we see in here for optical gain. And we also confirm that we see a threshold behavior at around this pump power level. This is at one wavelength. This is the integrated intensity. And as you go to a really high pumping power, you see the sharp lines show up. Actually, this red curve is already limited by the resolution of the spectrometer. With higher resolution, you can see very narrow lines. So this is a sign of lasing. So we think if we further improve that, we could do an electrical pump laser. So you turn on your switch, and this will laser. And then you can integrate many of these lasers on silicon at low cost. So as I promised, we can figure out the power consumption to transmit 1 bit of data with photonic approach. Photodetectors are practically almost zero power consumption because it's photovoltaic mode. Modulator is about 25 femtojoules per bit. The optical power used for bit error rate of 10 to minus 15 is actually determined by the performance of your photodetector. You calculate this one and all the loss from the modulator and waveguide and the efficiency of the laser. You still only consume 1 to 2 femtojoules per bit. So adding them together is about 30. While for electrical interconnect, from board to board, it's this number. It's 10 to the 5. From chip to chip, it's 10 to it's more like 10 to the 4. And core to core, for multi-core computer, average is 500. So overall, we can achieve about 100-fold efficiency enhancement for green information technology with integrated photonic interconnect. Okay, we'll shift gear a little bit, talking about photonic application in energy harvest and recycling. So this is the map for solar energy in the United States. So California and the southern states, of course, have more sun. Unfortunately, we're here, around here. But still, that's significant power. But if you calculate how much power you need per person, how large the solar panel should be, you find energy consumption per person in the United States about 11 kilowatts, and assume a commercial cell efficiency of 13%, every one of us need about 3,000 square feet to satisfy the power need. Okay, you probably don't want to view that in your, at home. And that also tells you that you really, really need to reduce the cost of solar energy. So that's why...
Can I ask you a question?
Yeah.
Is that total energy or electrical energy?
Electrical, yeah. So although the solar energy incident on the United States is about 500 times greater than total energy consumption, yet solar energy only contributes about 0.1% of total electricity. That's because of the high cost. So the key to success is higher efficiency, low cost. Let's look at the solar materials. So this is distribution of solar materials. You can see different flavors of silicon. For example, this red is a multicrystalline silicon, green is single crystalline silicon, this blue is amorphous silicon, and those add up to about 98% of the solar market. The other two competitive materials, cadmium telluride, about 1.6%, and CIS is copper indium selenide, which is about 0.2%. So why is silicon so popular as a solar cell material? The answer lies on the beach. So what do we have here? We have nice sunshine, like this. What we have here is our material, SiO2. So this is very abundant in the Earth's crust. Actually, silicon is the second most abundant element on Earth. Can you guess which one is the most abundant? Any guess?
Iron.
Answer is right here. Okay. So silicon is molecular weight 28, oxygen 16, 2 times 16, 32. So whenever you have silicon, you have more oxygen weight than silicon. And there are minerals without silicon that still have oxygen. Okay. So silicon is popular because this abundance of material, and also because of maturity in material and device processing that we inherit from development of microelectronics technology. That 60 years of development get us a lot of knowledge in silicon. So next time we go to the beach, bring a solar cell panel. think of making one, or if people really get to concerned about renewable energy someday, you can probably start a business of leasing these solar panels on the beach. Okay, so talking about reduce the cost, one way is do your thin film solar cells, because currently most of the solar cells is using bulk material that's usually wafer level 200 to 300 microns thick. If we reduce the material consumption with thin film solar cells, then we'll remove 50% of the bulk silicon cost. That is, we'll cut the cost at least by half. And there are additional gain in processing cost, because getting this bulk silicon, you need very hot furnace, above 1,000 degrees. While doing the thin films, you can now do plasma-enhanced chemical vapor deposition. It's the same tool, same technique you use in flat panel displays, very mature technology, and potentially can be very low cost. And because it's low temperature processing, you can even think about depositing this on a flexible substrate and paste it everywhere. So in terms of CO2 emission, you can see bulk silicon is already pretty competitive. If you reduce to thin film silicon, that will actually at least cut this by half, because you need less material. And all these advantages drive the boom of the thin film solar cells. So this thin film solar cells is the fastest growth factor in all solar devices. And the production is more than doubled from 2006 to 2007. And it's still keeping the strong growth in the solar industry. So this is the technology to go. However, there are limitations of thin film solar cells. Not only silicon, but other thin film solar cells. But silicon is a good example. For example, because of the absorption coefficient roll-off, beyond 600 nanometers, you find the absorption length will increase from 2 microns to 300 microns. So if you just absorb things with a very thin layer, you lose a lot of the solar spectrum, a lot of solar energy. So what can you do to fix this problem? One way is to get random surface texturing so that you can scatter light in lateral direction. Turns out this technique works really well for bulk silicon cells, but for thin film it doesn't work anymore, because if you get too much roughness, you increase the surface area of the semiconductor material. And I think it's Pauli who said, God created a crystal, it's demon who created the interface. So interface, you have many dangling bounds, many defects that will eat up the photocarriers to generate. So this technique does not work well anymore. You can get you a few percent increase in efficiency compared to a flat cell, but it's much less efficient. So here's the approach we propose. If you do nothing, the light will only go through one path. If we have a perfect reflector, this is distributed broad reflector. I'll talk about more detail in the next slide. You can get 2 paths. But as you get to a second pass, 70% of the light will leak out of the front surface again. So okay, this is actually I think it's more like direct calculation from the N1 minus N2. This is for relatively thick films without considering much about interference. So this is more like an average number that show for people to estimate. Okay. So, but if you have a backside grating structure, you can really diffract the light sideways. And as you hit the top of the surface, because this angle matches the total internal reflection angle, you can guide the wave in the sideways. That way you greatly elongate the optic path inside the material and enhance the efficiency. So what is a DBR structure? Distributed black reflector is actually a near perfect mirror. So if we make two materials, each one thickness having a center wavelength, for example in this case about 0.8 micron, and the thickness is this wavelength divided by 4 divided by the refractive index, you get a very broad reflection spectrum in the range that you need optical path length enhancement. So this blue curve is actually the theoretical calculation. This red curve is actually the experimental result. What you notice is this is greater 1. That can't be right. And what's the reason? Because the reference sample, the reference you use for getting reflection equal to 1 is based on gold. So people assume gold is a perfect reflector, but it's not. DBR is more perfect than gold. So if you make the structures measure reflectance, you can often measure reflectance greater than 1. So this tells you that this is a very efficient mirror. And for the grating fabrication, we used to do this complicated lithography to demonstrate the concept, but recently we're moving on to doing self-assembled structures. This is, many of you may be very familiar with this anodic aluminum oxide, which you can do with electrochemistry. You can control the pore size by the pore period, actually interpore distance by the applied bias. And once you have this period, here and there, you can enlarge the pores to the extent you want by further chemical etching. So combining these two, we also need the adequate design, because we can design the period of the grating, the thickness of DBR, and this is a design map for that. So if you only have DBR, you get 18% overall relative increase in efficiency. But if you choose your grating correctly to match the solar spectrum, you get 34%. So this design can be further improved to 50% relative enhancement with thinner, this transparent conductive oxide layer that's basically trying to allow the light through while also being conductive to collect the carriers. It turns out this material still have quite a bit of absorption loss. So especially when diffracted light is sideways, it's also tend to the effective thickness that the light travel in this TCO layer also increase. So you get more loss from this TCO layer. So if we can improve on this, we can eventually get 50% enhancement. So this is preliminary experimental result. With DBR, we demonstrate 14% enhancement. This is the IV curve, except that I'm flipping over the fourth quadrant because people want to see positive things for good. That's the solar industry was using this kind of chart. DBR plus grating, what we call texture photonic crystal structure, get 23% versus the theoretical ideal 34%. And this residual part should be able to improve with better fabrication process. And if you look at the absorption spectrum, you do see a significant enhancement in infrared range compared to the reference sample. That's confirmed our light trapping scheme. So the last topic, I briefly discussed about cost-effective germanium silicon thermal photovoltaics for waste heat recycling. So as we know, the sun is actually a heat source. The photosphere temperature is about 5,800 Kelvin. So that gives you a peak emission wavelength around 530 nanometers, which is green light. And that's why human eyes are most sensitive to this wavelength. In thermal photovoltaic, we are looking at furnaces we burn on the earth, in the factories, in the steel works. And that temperature is typically between 1,000 Kelvin and 2,000 Kelvin. Because your temperature is much less, your emission wavelength is much longer. That's in the near infrared regime. So you need a material other than silicon to absorb it. And currently we're using gallium antimonide, which has the adequate band gap. One thing to notice is actually the power density is much higher than solar. And the reason is not because you have a heat source more hotter than sun. It's actually because you get so close to it. So you can get a power density about 10 watts per centimeter square. So using a similar device as solar cells, but with a smaller bandgap material for infrared regime, we can convert heat radiation directly to electricity. And this power density can be 100 times higher than solar cells. So what's the problem in this case? Turns out gallium antimonide is very, very expensive material. We usually base this on a single crystal material, but a 4-inch wafer can cost you $1,500 or so. So if you calculate the dollars per watt just from the substrate contribution, that is pretty high. That is almost 100 times higher than the fossil fuel generation. So people are thinking about using germanium single crystal substrate, but still it's relatively expensive. So we have 6-inch wafer that cost $800. So still not very feasible. But if you can grow a very good germanium layer on silicon, although your efficiency is probably not so high as these two materials, but in terms of dollars per watt from the substrate, not including processing that is, it's only 20 cents. So it makes a lot of sense to do this germanium silicon thermal photovoltaic cells. So the device design is like this. Any semiconductor material will have a band gap. So for the wavelengths below the band gap, for the photon energy below the band gap, it's actually not going to absorb. So we're actually reflecting those photons back with a distributed Bragg reflector, as we talked about earlier. And then for the wavelengths we do absorb, we can get a filter to let it through, and then we convert that to electricity. And this reflective heat is not lost. It can further heat up the furnace temperature for a blue shifted spectrum so that you can generate more electricity from your cell, or you can decrease your fuel consumption while maintaining the same temperature. So one problem with germanium on silicon is that it tends to have a lot of defects due to this lattice mismatch. So germanium has a larger lattice, silicon has a smaller lattice. You grow one upon each other, then you tend to generate misfit dislocations. One way we found to deal with that is grow germanium on really small areas. You can get really perfect piece of germanium without any defect. So instead of making a large germanium silicon cell, we're actually dividing those into small areas, just like insect's eye, so that we can get more perfect crystal material. And even with this fabrication of this outside layer, we can still achieve much higher performance in terms of dollar per watt for these devices. Okay, to conclude, I hope I have convinced that nanophotonics will help to light up the future of energy, sustainable energy. We have demonstrated a 100-fold decrease in interconnect energy consumption for green IT technology. We have demonstrated efficiency enhancement and cost reduction for PV, that's photovoltaic or solar, and thermal photovoltaic cells. One thing I haven't have time to discuss is more efficient solid-state lighting. That's the white light LEDs you use now. And if you reduce the cost, that can also increase the efficiency of lighting. So with all this, I think it's very promising to see a bright future. Yeah, sorry, I forgot to acknowledge my sponsors and my colleagues, and also thank you all for attending. Any questions? Yeah.
So your 60% power consumption just walk with an interconnect is a really compelling number, but if I understood what you were saying correctly, that includes all the interconnects within the chip between gates, right?
Right.
Are you proposing to do electrical to optical and then optical to electrical between each gate on the chip?
At very short distance, like several microns, it doesn't make sense to do that because electrical is still effective. But if you're talking about core-to-core connection, especially we're thinking about this broadcasting of information across the cores, that makes the programming really much easier. Then it's much more efficient to do the optics.
Okay, so you think that's the sort of point of diminishing returns is between the cores within a single?
Yeah, and also programming issue because software engineers still investigating how to program these multicore processors. Yeah.
So I think from the perspective of sustainability, the key data point you talked about is cost effectiveness versus fossil fuels. So to what degree does federal policy influence your ability to do research in this field, and what sort of policies would you like to see put in place to help with that?
We should send you to Washington.
Probably going to be there.
So I think we absolutely need people like you because some of the barriers really people who attach to fossil fuels, who have their benefits in the fossil fuels, and also the government support. So for example, Germany was not a big country using solar energy, but the government really sponsored the solar research and usage of solar energy. So now they are currently occupy 40% of the world's solar market. So that's a big impact, I think.
Are there specific policies that you'd like to see?
I think apart from that, I think we just talked about that last night with some other faculty member. I think really need to let people know the importance of renewable energy, because no matter you say, okay, we still have 100 years of oil to use, one day it's going to be used up, and it's high time to develop renewable energy for our future. Yeah.
What limits the number of waveforms that can be in one nanophotonic wire?
Very good question. Actually, you should ask the elder lady right behind you, and she's the expert in this field. That's because we have too much power density in the waveguide. You start to see nonlinear effects, and that's the really limiting factor. But when you're doing a low energy photonic interconnect at around 100 to 1,000 wavelength range, you will not hit that bar. If you want to put more, then we have to investigate. Yeah.
I have a couple of related questions actually. One is, in what stage of commercial development are the thin film solar cells that we were talking about?
You mean commercial?
Yeah.
Commercial, I think people are putting a lot of efforts, like Applied Materials. They're experts in doing this plasma enhanced chemical vapor deposition tool. And in Germany, they have a factory that have capability of doing a panel 5 meters by 3 meters square. So that really make mass production a great possibility. Of course, if you further decrease the temperature budget of this process, you can even think of flexible substrate, and that will reduce the weight of your solar panel. So that will also improve.
So what kind of time horizon do you think that this would catch up on a big commercial scale?
Okay, this is a good question. I think it's related to technology development, but also the other things like policies and other competitive renewable energy sources. So I would say it's very hard to get a timetable, because people are trying to predict this. Some of them are really correct, so I wouldn't make the same mistake again. Yeah.
I have a question about a particular detail of your number for the bandwidth of the photodetector. I think it was 7 gigahertz. Was that
100, yeah.
Was that with bias or unbiased, and what kind of impedance was that?
That's based on the capacitance and possible series resistance of the device, because the intrinsic field effect is sub-picosecond. It's very fast. That can maybe go to terahertz, although people are still trying to measure how fast it is.
The measured data you showed, what circuit was that working into?
Oh, that was a device, but we have a trouble with one of the fabrication step. One of the layers etching, we etch off a heavily doped polysilicon electrode. So it's basically just a metal naturally touching. So we get a high series resistance there, and that compromised the bandwidth.
So that's what limited it, but the test setup for measuring that.
Oh, okay. It's also somewhat limited. We have a measurement setup for up to 10 gigahertz capability.
So was it a 50 ohm load, or into a short circuit, or an open circuit?
I think it's based. It's a 50 ohm load. I think it's based on 50 ohm load. Yeah.
Okay, no further questions. Let's thank our speaker again.
Thank you.